So when we learn double integrals, we were using them to, for example, find the volume underneath the graph of a function of two variables that lies above a region in the xy plane. So double integrals gave us a way of computing volume because they allowed us to integrate over a two-dimensional region, like a solid region inside the xy plane. So what should a triple integral mean? If I have a function of three variables and I want to try to come up with some way of integrating a scalar function of three variables, what should that mean? Well, again, some of the physics examples that we saw in the applications of double integrals yesterday can kind of help to motivate, what a triple integral can kind of tell us. If I have a function of three variables, maybe that function is telling me how the density of some solid object varies from one point to the next. Like maybe I have a plastic object that I 3D printed or something, and some parts of it are really dense plastic and other parts of it are hollow plastic or whatever. Or maybe, a chocolate Easter bunny or something like that, where the ears are solid but the rest of the head is hollow, that kind of thing. So we have a description of how density might vary in three-dimensional space. I can use a triple integral of the density, which is mass per unit volume, to figure out what is the total mass of that three-dimensional object. So that's just one example of a reason that we might want to use a triple integral. From a technical perspective, though, there's not really any difference in how we approach triple integration compared to how we approached double integrals. We're going to be able to set up an iterated integral that's going to have three integrals iterated in a row. Maybe a z integral, followed by a y integral, followed by an x integral, or something like that, depending on how we have tape measured the three-dimensional solid region that we want to integrate over. And it's actually that tape measurement process that is going to be a big new thing number one for us in the process. So just, kind of getting a three-dimensional object and figuring out how to bound, for example, z in between two functions of x and y, and then squash it onto the xy plane and give us a region in the xy plane to tape measure. And then maybe we bound that by bounding x in between two functions of y and then squash onto the x-axis and measure up the x-axis with constants, right? So that would be a dz, dx, dy way of measuring out a three-dimensional region. So that's going to kind of be the first skill that we'll wrap our heads around. And the second is that when we evaluate those iterated integrals on our way out, just as in the previous example where we were finding the surface area of the top hemisphere of a sphere, there was a place where we had an integral with a dx dy, and we found out that converting that integral into polar coordinates was a really valuable way to make the integral actually doable and get to our answer. That's going to happen a lot in triple integrals as well. If we convert from an x and y into an r and theta in the process, then instead of polar coordinates, we say that we've used cylindrical coordinates. So z means the same thing, but x and y transform into r and theta. And then there's one more system of coordinates that's going to give us the biggest new thing, I think, about triple integrals, and that's spherical coordinates that use a radius, a length, a distance from the origin in 3 space, and a pair of angles, a theta, which is the longitudinal angle from 0 to 2 pi, and a phi, which is the azimuthal angle of declension from the North Pole. And when I convert a integrand into spherical coordinates, and also tape measure that region in a spherical sense, so getting bounds on r, theta, and phi, how does dx, dy, and dz transform into a d rho, d theta, and d phi in that process? So the spherical coordinate piece of it, maybe we'll get to that today, maybe we won't. We might leave that for next class. I just want for us to have some practice with setting up a triple integral and going through that sort of tape measure process of how to do it.